So our first activation function is the sigmoid function. This sigmoid function is defined as, say, sigmoid of x is equal to 1 divided by 1 plus e to the power minus x. Shift and enter. Okay, so how do we code this in Python? First, let us import numpy as np. Shift enter. And then to define a function, we use def. Define sigmoid underscore function of x such that, say, z is equal to 1 divided by 1 plus np.exp of minus x. This should do it. And then what will this function do? It will give us the value, it will return the value of z. So let us seal this here, and if you want you can test sigmoid function, say, of 0.5. So the definition is already there, you will get an answer. This answer that you get from the sigmoid activation function is always between 0 and minus 1. So the result, the answer from sigmoid activation function is always between 0 and 1. You see 0.6 is between 0 and 1. Alright. So how do we plot this? Our plotting library is called matplotlib. Let us import matplotlib.pyplot as plt. See, in case any of these libraries is not installed, you can go to the Anaconda console and you can type pip install. So you have to type pip install numpy. So this is just a one-line install, and I don't think anybody else has plugin install easier than Python plugins or Python libraries. The input to this sigmoid function, let us have a linearly spaced input to this function. So we use linspace, which means linearly spaced, and this function is coming from, so linspace is a function. This function comes from numpy, so we say np.linspace. So from minus 10 to plus 10, take, say, 100 samples. So we'll improve on this. Just let us first. If you want, you can see these samples. So you see a lot of awkward looking numbers here, and there is a way to simplify this. So if you want a better result, let's make it 101 and then press shift and enter. So why this happens is because suppose you have between, say, 0 and, say, 3, you have 4 numbers. So 0, 1, 2 and 3. So these are total 4 numbers between 0 and 3. So with this logic, this should be 101 and not 100. So we took a linearly spaced input and put that into a series called as X series. Okay, and so what will be the output? The output series, let's call it output series, is equal to, this will pass through the sigmoid function of input series. Series is not a Python term here. You could have called this X numbers and output numbers. Press enter. If you want, you can also see what these values are. Now we will plot this plt.plot. So plot function exists in matplotlib, which we have imported as plt. Where's plt? Plt here. So to use the plot function, you have to mention plt. Plt.plot. What do you want to plot? X series and output series have to be cross plotted. Say using green, G for green and O for circles. And there you get the plot of the sigmoid. As you see, it varies from 0 to 1. We don't want to see points, maybe we want to see a continuous line. So let us see how to do that. Plt.plot. Provide the X input and the Y input output series. You can explicitly mention line width. Say line width is equal to 5, gives a good thickness. And then you can mention the color as well. So color is equal to Y for yellow. Let us see if this works. And I think that works very well. So our first activation function is over. How to plot that in Python, and this is called as sigmoid function because of its S-like shape, sigmoid-like shape. I want to mention something here. If you look at the sigmoid function graph, it is pretty, there is no gradient. It almost becomes very flat at the ends. So there is almost no gradient. There is almost no gradient at the ends, or say there is no slope. This is called as vanishing gradients problem. This is called as vanishing gradient problem. So this such kind of an activation function is a problem for neural networks once they are working, because they work on gradient search. Gradient is required for them to work, and at the ends you see that it saturates. There is no gradient. Yeah, so much for this problem. We will discuss this later in details. For now, our second activation function is hyperbolic tan. Hyperbolic tan, called as tan H. H for hyperbolic. Shift and enter. So at a certain point, we'll plot multiple, activation functions together and compare. So hyperbolic tan of any number x. First, let us write the formula, then we can code it. Hyperbolic tan of any number x is equal to e to the power of x. Say e to the power of x minus e to the power of minus x divided by e to the power of x plus e to the power of minus x. I used to love trigonometry, so I don't really mind this, but in case you don't, this already is perfectly okay. Very simple. Okay. So tan of x, hyperbolic tan of x is e to the power x minus e to the power minus x divided by e to the power of x plus e to the power minus x. Let us see how we can do this. Say import numpy as np. You may not need to do it again, but I just do it for being complete at the derivation. Say define this function. Let's call it hyperbolic tan of x, such that what does it do? It calculates a z value. Okay, this z is, as per the formula, np dot exp means e to the power of x minus np dot exp to the power of minus x. Yes, and then divided by np for numpy, np dot exp of x plus np dot exp of minus x, and shift and enter. Oh no, sorry, it has to return something. No, it will return the value of z. So now you can test it. Hyperbolic tan so let us try giving it anything. So this works. Again, our input has to be linearly spaced, starting from minus 10 ending on 10, and let us take 101 numbers. Shift enter. The output series will be found out by sending this input into hyperbolic tan function. Let us call this output series 2, and this will be hyperbolic tan of the input series. Oh my god. Shift enter. Name hyperbolic. Yeah, it has to be hyperbolic. Hyperbolic. Yeah. Check if that's worked. Pretty numbers. All right. Let us invoke our plotting library matplotlib.pyplot, and to use our functions from matplotlib we will be using plt. Then plt.plot, input is x series, output is output series 2, and line width we can say is 5. Let's see if this works. That seems to work, but you see the vanishing gradient problem is still there. Can we plot our first and the sigmoid function and tan function, can we plot them together? Before that, if you see, there's one subtle difference. With sigmoid function, the output range is from 0 to 1. With the hyperbolic tan, the output range is between -1 and +1. Let's see how we can plot these together. So plt.plot series, output series was the first output, and they share inputs, but outputs are different. output series 2. So we plot these together and let us see if line width specification also can be mentioned or not. We will check this. Okay, so system should automatically color these two differently, and that's what happens. So you see in blue you have the sigmoid function, and in orange you have the hyperbolic tan. So we are already done with two of our activation functions. Our third activation function, our third activation function overcomes the vanishing gradient problem posed by the above two graphs. So our third activation function is called as rectified linear unit. Rectified linear unit. RE for rectified, LU for linear unit, ReLU. So ReLU of X, I don't know if they pronounce it like that, but it's okay for me. Rectified linear unit, ReLU. So how do you define this? You say define ReLU of X such that it will return. So it computes some z and returns that z. Return maximum out of 0.0 and x. So that is our definition. Give it any number, it will put this number into this function and check and return either 0 or x. Let us test this rectified linear unit. So you can put in any number in this ReLU function. Let us put minus 0.55, whatever. So x was minus 0.551, and what is the maximum number out of 0.0 and minus 0.551? So you get 0.0. Rectified linear unit of 5. It calculates maximum of 5 and 0, you get a 5. So this works. Again, we import numpy as np. We define a series of linearly spaced numbers starting from minus 10 to 10, and that's our input. Our output series, let's call it output series 3, is equal to rectified linear unit. So this is like writing a loop in Python. So I will say rectified linear unit of, say, I. You can write I, or I prefer to write each x actually. Even in Java or C#, I prefer to write each x instead of I. So ReLU of each x for each x in the input, which is x series. This is like the for each loop, in Java, or for each loop in C#. So for each I in x series, put that I into ReLU function, ReLU function. Alright. Invalid syntax. Wow. ReLU of each x or each x in x series. Yeah, so I figured out I left a space here. That syntax is not valid anywhere in any language. Alright. So output series 3 is such that you put each of the numbers in x series into ReLU function. If you want to see the output, you can actually see that. Shift, Shift Enter. All right, sweet. Now let us plot this. Put matplotlib.py plot as PLT. The X series and the output series 3 are cross plotted with a line width of 5. So this happens to be our third activation function, known as Rectified Linear Unit, and it's a very simple function. Here it is, and as you see, there is no, the gradient is not vanishing. There is a constant gradient here. So this is better than the sigmoid function and the tan h or the hyperbolic tan, but there are problems. This has its own problems. It has a problem known as exploding gradients. So this activation function, rectified linear unit, has its own problems, like exploding gradients and dying neutrons. Dying neurons. So we will cover this later. So, as if a neuron is stuck on the negative side and then the output happens to be 0. So that's called a dying neuron. And because of these problems, there have been more functions revised, the activation functions. Our fourth activation function is known as Leaky ReLU. So our fourth activation function is called as Leaky Rectified Linear Unit. Let us define this. So define leaky rectified linear unit of X such that it returns you maximum of, so this doesn't return you maximum of 0 and X. So there is a small multiplier that has been introduced, 0.01 times X, and then it is compared with X. So slightly different from ReLU. Shift Enter. My biggest problem with Python is pressing these two keys, Shift and Enter together, but I think I'm getting used to it. All right. Leaky rectified linear unit. Let's test this now. Put some numbers here. Seems to be working. Then leaky rectified linear unit of minus 0.6. So you see, this has multiplied our number with 0.01 and given us 0.006. So this works fine. Let us plot this. So every time I write this, because many times when I'm working I have to go away and my Jupyter Notebook doesn't really remember what I done earlier as for the inputs. So we have imported numpy, and then as usual, this is our fourth activation function, the leaky ReLU. We will define the input again on the regular 1D grid, linearly spaced. And this time the output series, let us call it as output series 4. Please don't leave any space here. Alright. This time Leaky rectified linear unit of each x, you can write an I or a j. I prefer writing each x. For each x or every x inside in x series. So take every x out of x series and put this into Leaky ReLU function. So this has to be an array in itself. Output series 4, we can view the results. That works. Now the plotting part. Import matplotlib as PLT. Matplotlib. Let us plot two functions together, the ReLU function and the Leaky ReLU function. plt.plot. So rectified linear unit was stored in output series 3 and the Leaky rectified linear unit is saved in output series 4. And to distinguish them, you can define your own colors, say magenta, and the line style as well. So I want to plot my ReLU function in M for magenta and this dash fashion, and for the Leaky ReLU I want a yellow color graph, and for both of them I want line width equal to 5. Let's see if this works. Yeah, so you see there is a slight difference here, absolutely slight difference, not very much, but this may be significant when a neural network is actually relying on them. So I save this Jupyter Notebook, and we have done 4 of our activation functions: Sigmoid, Hyperbolic Tan, ReLU, and Leaky ReLU. After ReLU and Leaky ReLU, which happen to be almost similar in the graph, slight difference, our fifth activation function is called ELU, or Exponential Linear Unit. Exponential Linear Unit. So here we can provide an additional alpha value. You can provide here an additional alpha value. This alpha, so we will test common alpha values of 0. So can be 0 0.1, 0 0.2, 0 0.5, 1, 2, and so we will plot some of these. It's generally 0.1 or 0.2. So we will test some of these values. Let us start how to plot ELU, or Exponential Linear Unit. As usual, import numpy snp, shift enter. Let's define the ELU or ALU, I don't know, ALU of X. So this function, oh no, this is an additional parameter, which is the alpha value, which needs to be supplied by the user. So definition of this exponential linear unit, it says if x is less than 0, so on the left hand side of the graph, this is what it does. It returns your supplied alpha value, it multiplies with e to the power x minus 1. Alright, so now when we are writing this function, it's very important not to mess up the indentation. Suppose I change the spacing here, the function will not work. So Python will recognize only nicely indented functions. It will tell you in the error, if it's not able to uh, understand your function because of poor indentation. Not really poor, but a strange indentation. For x being positive, just return x, and that's our function. Shift enter. So let us test this function. Say minus 0.5 is applied with a number, alpha value is 0.2. Seems to be working. And let us also test this for a positive number and an alpha value of 0.2. Alright, so if you give it a negative number, it is going to multiply the alpha value with e to the power that negative number minus 1. Otherwise, for positive numbers, it's going to return you the same number. So when I gave it a 7, it throws it back. It gives you the number. Let's define the x series. And the output. This is our, I think, fifth activation function. So output series 5 is defined as, so in the GELU function, put I or each x, every x, but the function has an additional parameter. The parameter is a, the alpha value. You have to supply that alpha value here. So 0.2, sorry, 0.02 for each x, in x series. So there is a number series of inputs. Take each number, put it into the GELU function with an alpha value of 0.02 and evaluate this. So this becomes my output series 5. But remember, we said we'll be testing a lot of numbers. So I started from 0.2. Let's go to 5. So output series 6. We'll skip something, otherwise it will be too much. Let us test each x and say alpha value of 1 for each x in x series. So we'll be drawing the output when alpha is 0.02 and alpha is 1. And let's add a few more. So we define ELU function with x and an additional parameter. That additional parameter, let it be 2 now. And finally, let us almost take a huge number. Let's put a 5 here. So we can just copy paste. This time use 5. Now we are in a position to plot all of these. plt.plot, use x series with output series 5. So 1, so alpha of 0.02. Similarly, output series 6 alpha 1, output series 7, which is alpha is equal to 2, and output series 8, which is alpha equal to 5. Let us mention the style, and you can write line style equal to, within single quotes use dashed, and line width is 5 as usual. So we have many graphs here. The blue one is alpha 0.02, the orange one is alpha 1, green is alpha 2, and this strange one is alpha is equal to 5. So this is our fifth activation function, very popular, and this is called as ELU of x or LU of x. Now we'll code our sixth activation function. Is has a swag, it's called Swish. Swish function is defined as product of number x with sigmoid of that number. So x times sigmoid of x is known as Swish function. Let's code this. Say import numpy smp, shift enter. Define Swish of x such that it will return you x times or x divided by 1 plus e to the power of minus x. So 1 divided by 1 plus e to the power minus x is your sigmoid. We multiplied that with x, which is effectively x by 1 plus np dot exp to the power minus x. That is our Swish function. In regular fashion, linearly spaced input. So you repeat this so many times that you will remember. Okay, once you do this exercise, no need to do anything. The activation functions are done. And then let us store this in output series 9. So the output should be output of Swish function for each of these x in x series. I think we are good enough. Now we will plot. Import. plt.plot. Mention the line style and mention the line width. So you see this slight depression here. This is your swish function. There's no vanishing gradient problem. So this we are done with our sixth activation function, and only one more we'll be covering in this lecture. The last activation function that we'll be covering is known as Gaussian error linear unit. So number 7 is Gaussian error linear unit, GELU, always. So this is the activation function used in BERT algorithm for Google search. This is the latest. This is one of the latest. This is used in BERT algorithm in Google search. BERT means bidirectional encoder representations from transformers. So this is just general knowledge, BERT is bidirectional encoder representations from transformers. Oh man. So said simply, when you're searching something on Google, the context matters, right? For example, you can say we went to the Thames River bank for a photo shoot, right? So when you say we went to the Thames River bank for a photo shoot, Google search has to know that this is not a bank where you're going to deposit money. No. So the context matters, and Gaussian error linear unit is something, sorry, BERT is something, this BERT algorithm, it is a bidirectional algorithm. So this can capture context from left as well as from right. So it will capture we went to the Thames River, also it will capture for a photo shoot. So this is the context for saying the keyword bank, and it matters for Google search. So GELU is an activation function which is used in BERT, and BERT is bidirectional in terms of context. It can read, understand from left to right as well as from right to left. So now GELU is defined by a very scary looking function. So GELU is defined by a strange, it's a heavy formula, man. GELU of X, I don't think anybody can remember this, but alright. 0.5 times X, and then there is a hyperbolic tan inside. Hyperbolic tan 2 divided by pi, and the whole thing multiplies with x plus 0.44715 into x cubed, so x to the power 3. Man. Alright, so much for maths. Let's code this. Coding is easy. Import numpy smp. let us import matplotlib.py plot. Define the GELU function. GELU of x such that it will compute a z or z in American English. Z is equal to 0.5 times x, and this is multiplied with 1 plus hyperbolic tan of 2 divided by np dot pi. So pi becomes np dot pi. And that number is to be multiplied many times. A small problem in the formula can totally wreak havoc on the results. It happened to me earlier, so be very cautious with x plus 0. See, I already wrote it wrong, so this is 0.04. 0.044 0.044715 and x cubed. So x cubed is x times x times x. Good heavens. Alright. Oh, it has to return. Let's see. Return C. Now we're going to plot this. So there has to be an output series. So the output series, number 10 this time, there is a GELU function. Put each x, GELU each x for each x in x series. Now x series I've been defining everywhere, so I think it should take it. Alright, this has to be enclosed in square brackets. It's been a long time, maybe let me write that. So x series is equal to linearly spaced numbers from minus 10 to plus 10, 101, and should work now. Yeah, so I figured out I have to put a multiply sign here. Shift enter. Yes, so there has to be a multiplication sign between the brackets and x. That was fine. Alright, now I should be able to plot this. So plt.plot plot x series with output series 10, and let's use blue color. Line width of 5 as usual. We'll be comparing it with earlier functions as well, but for now, alright. So this to me looks very similar to what we saw in the Swish function. Yes, so Swish function, the depression, it seems very similar to what you see in GELU of x. So maybe we should compare these two, and plt.plot Swish was in output series 9, and this one is in output series 10. You can say line style to be equal to dashed. You can actually type dashed. And line width we've been keeping as 5. How different are these? Slight difference, and maybe only in this part, so maybe we should limit our plots. Let's put limit on our plots. So x limit, say from -3 to +3, and similarly y limit also from -3 to +3, and we should be able to see some difference. Yeah, so you see the Swish function and the GELU function are quite similar, but not really. And that brings us to the end of this uh, demo with the most common functions. So what all did we see? Yeah, we saw sigmoid, then after sigmoid we saw hyperbolic tan, rectified linear unit, and we also saw Swish function. We saw leaky GELU as well. So we saw leaky GELU, Swish, and then GELU. Thanks for watching. Thanks a lot.